Now let's discuss another example for the application of grand canonical ensemble formalism. Here we have a system of harmonic oscillators. And now you know that a system of harmonic oscillators can be regarded as independent particles like atoms in a solid, or independent particles like atoms in a solid can be treated as a system of harmonic oscillators, in other words. Now we will do one thing. We will be going after a general derivation up to some step without mentioning whether it is quantum harmonic oscillator or classical harmonic oscillator, and thereafter by proper substitutions you can get the result for classical as well as quantum harmonic oscillator. So let's begin as usual. In the case of a system of harmonic oscillators like particles or atoms in a solid, the particles of the system are localized in their sites. Any atom in a crystal, they are localized at their own lattice sites, and hence they can be treated as distinguishable. So that is a first thing that we have to consider. So since the particles are localized, we had discussed the same conditions or same idea during canonical ensemble application. Localized at their respective lattice sites, they can be treated, means the particles can be treated they can be treated as distinguishable. And what is the immediate consequence of this concept? That is, in the definition of the partition function, we need not account for the indistinguishability, or we need not do the Gibbs correction, since the particles are assumed to be distinguishable. So that is the immediate result of our assumption that the particles are distinguishable. Now therefore, as usual, we will be writing first the canonical partition function of the system. Therefore the canonical partition function of the system, and from which we will be writing the grand canonical partition function of the system, is given by, we are writing it as Qn of Vt. Avoid writing Qn of Vt and all. That's Qn is equal to, simply that will be related to the single particle partition function, that is Q1 raised to n. So that is equation where this Qn is nothing but our usual Qn of Vt. That's understood for the for the canonical partition function. We are writing it simply as Q1 raised to n. Now just compare this equation number 1 with the equation number 1 that we have written for classical ideal gas. There the particles indistinguishability was causing a problem of Gibbs paradox. In order to correct that one, we divided this one with n factorial. So that n factorial is missing in equation number 1 in our case, because we have treated the particles to be localized at their lattice sites, and thereby they are treated as distinguishable. So that is a notable difference between the classical ideal gas discussion and the system of harmonic oscillators that we are doing right now. I hope that you have just understood that or noted that. That's a notable point. Now since the particles are localized, we can write the partition function Q1 should be independent of the volume available to the system. Is it not? So that is an immediate consequence of this assumption. Since the particles are localized, like an atom is fixed in a crystal lattice, then the volume of the lattice doesn't make any effect on the degree of freedom of the particular atom or thing. So since the particles are localized, the partition function Q1 should be independent of Q1. The single particle partition function should be independent of, there's an immediate consequence, should be independent of the volume. Whatever be the volume, that is not going to affect, because particles are anyway localized. independent of the volume of the system, volume available to the system, that is, I can write what is the dependence of Q1 on volume, that is Q1 is proportional to, we can say Q1 is a function of V and D in general, so I can write Q1 is proportional to V raised to 0, right? So the dependency is neglected, right? Therefore I can say Q1, which should have been a function of V and T, now Q1 proportional to V0, so Q1 can be written therefore merely as a function of what? Temperature alone. So I'm defining a new function now, phi, which is a function of temperature alone. So that is our assumption, phi of T. Where what is phi of T? Phi of T is a function of temperature alone, a function of temperature of the system alone. Hope you remember in the discussion of classical ideal gas application, we have defined a similar function f of t. F of t was defined as a function of temperature alone. Now in place of f of t, we are just naming it as phi of t. Okay, in order to distinguish it, we are calling it as just phi of t, where phi of t is a function of temperature alone, whose general nature can be assumed later. So you got Q1 and also you got Qn by equation number 1. Now we are in a state to define the grand partition function of the system. Therefore the grand partition function of the system, can be written, can be defined in terms of the canonical partition function. That is script letter, this is a symbol, by the time you must be familiar. Z is equal to sum over, how did you write that? We can write it in terms of the fugacity, that is sum over NR equal to sum 0 to infinity, then the fugacity is Z raised to that NR, Z raised to NR, then see the canonical partition function, that is what? QNR, right? Which can be again substituted, that is sum over NR is equal to 0 to infinity, sum over NR equal to 0 to infinity, Z raised to NR times QNR. What is QNR? QNR is given by equation number 1. In place of N, we are substituting, what is that? NR, and in place of Qn, we will be substituting phi of t. That's all. Okay, so I can write this is nothing but phi of t raised to NR, right? And both Z and phi of t are having the same power, so I can just simplify this one as NR equal to 0 to infinity, Z, I'm combining the fugacity Z and phi of t, whose exact nature is not substituted so far, raised to NR. Okay, and hope you remember we had arrived a similar step in the case of classical ideal gas also, where we used a series expansion. Okay, and here also we are going to depend on a series expansion here. So we call this one some equation number 3 or something like that. Okay, so there is a result that sum over you can write, there is a result, series expansion result, that is sum over n, some running index n equal to 0 to infinity, x raised to n, okay, which is of that form. Equation number 3 is of this form. It can be written as 1 divided by 1 minus x. This is a result. Okay, so since this is a thing, I can write equation number 3 as, considering the quantity in the bracket z into phi of t as x, we can write the grand partition function z is equal to 1 divided by 1 minus x, 1 minus z into phi of t, 1 minus z into phi of t. So this is our z finally, equation number we called as 4. And remember, in the classical ideal gas discussion, we had used another series expansion. So where there was one n factorial also. So since there was an n factorial, we got that is equal to, that series expansion is equal to what you call e raised to x. So instead of that, here we are getting this series expansion without n factorial in the denominator of x raised to n, we get it equal to 1 by 1 minus x. Okay, these are some classical results that we are using from or borrowing from mathematical physics, series expansions. Okay, so having obtained the grand partition function, we can define what? we can define the Q potential of the system, which is nothing but a part of the recipe of grand canonical ensemble formalism. And from the Q potential of the system, we can obtain all the necessary thermodynamics of the system. So let's go and define the Q potential of the system. Therefore, the Q potential of the system, please compare the earlier discussion always. So comparison will tell you a lot of simplicity. It will give you a lot of relief while you discuss or while you refer to this derivation. Q potential of the system, we can write Q is equal to the logarithm of Q is equal to log of that Z, which is further is equal to PV by KT. Of course, by definition, Q is equal to P by KT for any system. Okay, irrespective of whether it is classical harmonic oscillator or classical ideal gas, it is PV by KT for any grand canonical ensemble system. So it's log Z. So can you write log Z? Log Z means Z is equal to 1 by 1 minus Z phi of t. So that is equal to, that is a log, I can write Z. Z is substituted as 1 divided by 1 minus the fugacity Z into phi of t. Okay, so you have to take the log of this one. That is equal to, once again, PV by KT. I'm writing on the right side, that is PV by KT. Let's modify this one again. How? Log A by B is log A minus log B. So this one will reduce to, I can write this is equal to minus log, right? Minus log 1 minus Z phi of t. Now I am writing simply Z of phi. Z into phi, because phi is a phi of t. Okay, that is equal to PV by KT. That is equal to PV by KT. Now, therefore, I can get the pressure of the system, that is pressure of the harmonic oscillator system or system harmonic oscillator, can be obtained as on cross multiply minus KT by V, then log of that quantity, log of 1 minus fugacity Z into phi as a function of t. So that gives you the pressure of the harmonic oscillator or system of harmonic oscillator. We call it as equation number 5 for the time being. But I think while we discussed the harmonic oscillator in the case of canonical ensemble, you got a standard result which was worth remembering. What is the pressure of a system of classical ideal gas or harmonic oscillator? We obtained the result to be equal to 0, right? The pressure of harmonic system is obtained equal to what? 0, right? So here, but we are getting as non-zero result. How can it be true? Because we have seen that in the thermodynamic limit, both the canonical and the grand canonical ensemble must give you the same result, but here we are getting different results. Let's see how whether we'll be able to get the result, standard result of pressure equal to 0. Okay, for that you have to the thermodynamic limit. So you know what is meaning by thermodynamic limit. In the thermodynamic limit, you know what's the meaning? That is the volume tending to infinity, right? Volume tending to infinity. So as volume tending to infinity, you can see that equation number 5 will give you the pressure will be tending to 0. What it? Because volume is in the denominator. So if the volume tends to infinity, then of course the pressure will become what? Tending to 0, or we can say that pressure equal to 0, which is the standard result. So this is something that we have already mentioned. The grand canonical ensemble or canonical ensemble, you can apply it for any systems. Okay, depending on the mathematical convenience, whichever is convenient mathematically, you can apply it to any system. But in the thermodynamic limit, the results should converge. All the results should be converging. That should be verified. So which is the standard result. Okay, remember here that T and Z are intensive variables. So T and Z are being intensive variables. As V tends to infinity, it is not going to be affected. The intensive variables will remain the same on changing the volume. So we need not bother about what will happen to temperature and Z, the fugacity, as volume tends to infinity. Okay, so that is the thing, right? So that is proved. One standard result is established. Now we can similarly we can get other quantities also, thermodynamic quantities like average number of particles. N bar or N is equal to, that is the equation is Z dou by dou Z. By the time I think you should be familiar, of log Z dou by dou Z of log of, okay, that is Q potential. Okay, so which can be written as it's equal to Z dou by dou Z. Be clearly distinguishing the two Z that we are writing. The small letter Z with a cut here, I mean the fugacity, and the capital letter script letter Z denotes what? The grand partition function in all these cases. So you can substitute for log Z, that is equal to minus log of 1 minus Z into phi, 1 minus Z into phi. Okay, which you can do, that is equal to, I can take that minus sign outside, minus Z dou by dou Z of, right, log of 1 minus Z phi. Okay, which you can do, what will be that? It's equal to minus, okay, minus Z dou by dou Z of log of a function, that should be equal to 1 divided by 1 minus Z phi, 1 divided by 1 minus Z phi into function rule you apply it, so it will be equal to minus phi, right? So that will be multiplied with the minus phi. So minus minus, it will become plus. Finally what you're going to get is n equal to Z into phi. Phi is a function of time, of course, let me bring it back, divided by 1 minus Z phi of t, 1 minus Z phi of t. So that gives you the average number of particles for a harmonic oscillator system using grand canonical ensemble. We call it as equation number 6. Similarly, you can get the internal energy. The internal energy of the system, these are all thermodynamic quantities of interest. Internal energy of the system, internal energy, U is equal to, simply that is equal to kT square dou by dou T of, these standard equations has to be remembered, that is log of grand partition function or Q potential. So that is equal to, you can just substitute, that is equal to simply kT square dou by dou T of, you have to write, what is that, minus log 1 minus Z fugacity into phi of t, where phi of t is a function of temperature alone. Since this dou by dou T means I have to treat Z and V as constant. Z and V is treated as what? Constant. So that can be simply written as, it depends on the exact form of phi of t, so you can simply write as it is affected only by that one, kT square into dou by dou T means it will be logarithmic function, it will be equal to what is that, 1 by that equation, so it is 1 minus Z phi of t, 1 minus Z phi of t, that will be coming in the denominator, into then function rule. See what will happen, that will be yes, there is already a minus sign is already there. Then there will be one more minus sign when you take the derivative of this one with respect to temperature, so that we minus Z, right, minus Z into then derivative of phi of t, I can say phi dash of t, you can, let's call it as phi dash of t because exact form of phi of t is not taken. So this minus and minus will be getting plus, so finally what you're left with is nothing but kT square Z phi dash of t, kT square Z phi dash of t divided by 1 minus Z phi of t. So that gives you the internal energy of a harmonic oscillator system in grand canonical ensemble formalism. Okay. Similarly, you'll be getting the expression for Helmholtz free energy. A will be equal to minus kT. We are writing it from the previous standard result, plus nkt log Z. This was our standard equation for grand canonical ensemble, which you can substitute nkt. I'm writing the second term as first term, plus kt into log. So log Z can be substituted as what? Minus log. Okay, so that minus and minus will become plus, so minus Z phi of t. So if phi of t is known to us, you can just substitute. Similarly, you will be getting S, entropy S is equal to, so by the same token that we are done in the case of classical ideal gas, U minus A by T, you can finally prove that it is equal to some lengthy expression nk log Z, nk log fugacity minus k log, you need not memorize any of this equation if needed. Okay, you can just substitute other thing, remember the recipe and get it, phi of t. Then plus what you get finally is that kt Z, it's all interrelated, phi dash of t divided by 1 minus Z phi of t. You are getting it from U with the expression for t. So that will be the expression for what? The entropy. Now these are some okay, you can call it as some equation number 8, equation number 9 likewise. So now using all these equations which are derived without telling whether it is a classical case or a harmonic, or a quantum harmonic oscillator, you can get the classical result and the quantum harmonic oscillator result by proper substitution. Okay, so that I'm leaving as a task for you to try on. See, not so just I'm giving a hint. Substitute phi equal to kt by h cross omega. Phi equal to kt by h cross omega. You know, phi is a function of temperature alone, so you can see that, which is nothing but phi of t. Okay, so if you substitute phi equal to kt by h cross omega as a special case into these equations, what are the final equation that we are derived? Okay, we can get the result for a system of one-dimensional classical harmonic oscillators. Okay, so that is one thing. Now for getting quantum harmonic oscillator results, substitute phi of t is equal to, in place of that phi of t what you have seen there, you substitute phi of t is equal to 2 sine h hyperbolic h cross omega divided by 2 kt. So depending on the way in which you take the functional form of phi of t, which was defined as a function of temperature alone, you can reach the results for harmonic oscillator, quantum harmonic oscillator and what, classical harmonic oscillator. So raised to minus 1, we can get the results, the thermodynamic results for quantum one-dimensional harmonic oscillator, which okay, if time permits, you can try it out. It's done in many reference books, you can refer to it. Okay, or see the derivation for quantum and classical harmonic oscillator has been done separately in many of the books. You can refer to that one also. And I find our current discussion to be just simple in terms of the methodology that we are following. So I just continue with the same methodology. Okay, so this is regarding the applications of grand canonical ensemble formalism to two of the familiar systems. Now we are left with one more topic, one more standard topic in grand canonical ensemble. With that we can conclude the module, and that topic is density fluctuations in grand canonical ensemble. Okay, you know, density fluctuation means the number density, the fluctuation in the number density, because we have seen that the number and energy both are variable in the case of grand canonical ensemble, and we have discussed energy fluctuations in canonical ensemble. So the similar topic in grand canonical ensemble would be the what you call density fluctuations in grand canonical ensemble, which we will be doing by the same token that we have done for canonical ensemble energy fluctuations by the method of mean square fluctuation in number, and after taking what you call the relative root mean square fluctuation in the number. The same type of derivation we'll be adopting. I think I will be just doing it as a separate lecture, which you can refer even, and we'll be getting similar type of results in the thermodynamic limit. We will see that the relative root mean square fluctuation in the particle density of the system in grand canonical ensemble is of the order of 1 by root n, which is negligible in the thermodynamic limit. Okay, so that's all. Thank you.